for this computer use. And then, yeah, it's pretty rich. Yeah.
Thank you. Okay, let's get started. Today's lecture is about crude fat analysis. Did you have the lab or? Oh, okay, great. So let's start with a recap on your information on food chemistry. Which sentence is correct? The term liquid can be used for both oil and fat. Oil has higher melting point than fat. Fat has less saturated fatty acid as compared to oil. What do you think? Yeah. A and B. Okay. So you chose A. Just A. Any other answer? Okay. Yes, just A. The term liquid can be used for both oil and fat. You know that animal lipid is called fat, and non-animal lipids are called oil. Why? Because in fat we have saturated fatty acids, more saturated fatty acids that make their boiling point higher, or melting point. But in oil, which is for vegetables, nuts, we have a lot of unsaturated fatty acids that makes their physical appearance, their physical characteristics as a liquid, which we call oil. And the melting point is lower. So A is correct. The lipid portion of the food can include vitamin A and D, consists of fractions with varying polarity, cannot be completely extracted using ethyl ether or diet. What do you think?
I was also make A
and B. Okay. Any other comment? Yeah, you go, please. A and C. Yes, all of the above. So, you know, we have simple fats, we have compound fats, and we have derived fats or lipids, sorry. Vitamin A and D are type of derived fat, lipids. And yes, lipids have varying polarity. Some of them, like triglycerides, are completely nonpolar or hydrophobic, and diglyceride, they are a little bit more polar. Phospholipids or glycolipids are more polar, so they are different in their polarities. And then, since they have different polarities, we cannot say one specific solvent can extract all the lipids completely. Why? Because they have different polarities. Triglycerides are completely nonpolar. Glycolipids are polar. Phospholipids are polar. So they have different polarities. So all of the above is correct. Can you define lipid? We talked about it. You learn about it in food chemistry. So, okay. lipids, since they are really, really diverse, they don't have specific definition unless they have a characteristic that they are not soluble in aqueous solution in water, but they are soluble in organic solvents. This is the only definition that we can present for lipids since they are really, really diverse. But if we want to classify lipids, we can say there are three main categories for lipids: simple lipids, compound lipids, and derived lipids. Simple lipids are a series of fatty acids. So you have an alcohol like glycerol, and then let's start with triglyceride. You have three fatty acids that ester to glycerol. And then you can have diglyceride or monoglyceride and other esters like wax. So with waxes, we don't have, instead of glycerol, we can have other alcohols. So they are, again, very, very diverse in their type. Compound lipids like phospholipids, glycolipids, and cerebroside. So again, you can have different chains here or different groups here. Or this one, glycerol, can be different, like in glycolipids. And then derived lipids like fatty acid, vitamin A and D, hydrocarbons, fat-soluble vitamins like vitamin A and D. So, why should we care about fat analysis? Why is it important to us? Yes. Yes, one important thing, we need to know how much cholesterol we have in our sample, if how much vitamin A or D, how much triglyceride we have in our sample. So nutritional labeling is one important aspect we need fat analysis. Yes. Shelf life estimation or stability. Yeah. Okay. So nutritional labeling, we talked about it. Regulatory requirements. We have whole milk, we have fat-reduced milk, we have non-fat milk or dairy products. So if you want to label a product as whole fat or non-fat or fat-reduced product, milk, cheese, or whatever, then we need to know the fat content of that product. Otherwise, we cannot say, okay, it's a whole milk, or it's a whole fat, whole milk cheese. And manufacturing specifications. Sometimes we want to sell an ingredient. So the buyer needs to know, okay, how much protein that ingredient has, how much fat content of that ingredient is. So we need to know the fat content of that ingredient that we are selling. So manufacturing specification is another important factor. And then stability or shelf life, because lipids are really, really susceptible to oxidation, which you studied about it in food chemistry. Methods we can use for fat analysis. We can divide them into three main categories: solvent extraction methods, non-solvent extraction methods, and instrumental methods. Solvent extraction methods, depending on the method, it can be continuous, semi-continuous, or discontinuous. A common continuous method is Goldfish. Semi-continuous like Select, which is an AOAC method. Discontinuous like Mojo or Mojonnier, which is again an AOAC method. Elevated pressure temperature methods like supercritical fluid extraction and accelerated solvent extraction method or AS. Non-solvent extraction methods like Babcock and Gerber, and instrumental methods like RIR, NIR, NMR, and Coslet methods. None of the instrumental methods are AOC method. AOC method is Succinylate and Mojo. So before we do fat extraction and fat analysis, good fat analysis, we need to do sample. The same as other proximate analysis we do. First step is sample. It depends on type of the food and nature of the lipids. And then, based on these, we need to choose the extraction method. If your sample is a dairy sample, it's dried, it has some moisture, a wet sample, it has high amount of carbohydrates or protein, then the method type will be different. And then we need to do appropriate sample and choose an appropriate extraction method. So, what do you think about it? To extract and analyze fat contents in a food, the sample preparation may include pre-drying, acid hydrolysis, particle size reduction. Yes? All. Any other? Yes? A and C. Okay. All of the above. Pre-drying. If you are going to do fat analysis using Succinylate, you need to do pre-drying on your sample. Your sample should be dried. Acid hydrolysis. If you are going to do fat analysis using Mojo, then sometimes when the carbohydrate content is high, you need to do acid hydrolysis. Particle size reduction. It's almost a rule for sample preparation for many proximate analysis. If you have a grain, if you have a non-homogeneous sample, you need to grind it, to mill it, or anyways, you need to make it homogeneous in terms of shape and size. Size reduction also provides higher surface for extraction. So when you have smaller particles, the surface you provide for solvent to extract fat is more. So you will have a more efficient fat extraction, or better to say, fat analysis or fat content measure. So all of the above, yes. So the first group of fat analysis were based on solvent extraction methods like Mojo, like Succinylate, Goldfish. So when we want to choose a solvent for these methods, we need to pay attention to a few parameters. First, if we have protein or carbohydrates in our sample, which solvent should I choose? Solvents should have low boiling point. Why? Because we need it to evaporate, and then we can weigh what is left, which is fat, and determine the fat content. Solvents should be non-flammable, non-toxic, inexpensive, of course, And then non-hygroscopic, hygroscopic means a compound that absorbs water a lot, moisture a lot. So non-hygroscopic, it's important. Otherwise, the solvent lose its efficiency over time. Is there any solvent with all these characteristics? Do you know any solvent that has all these characteristics? Yes, not really. There is no specific solvent that has all these characteristics. So what can we do? Probably we should choose combination of solvents that work for us. Let's compare two common solvents, ethyl ether or diethyl ether and petroleum. So ethyl ether, it is not completely nonpolar, so it's a common solvent for extraction of lipids, a common solvent. It's more, but petroleum ether is completely nonpolar, and it's good for extraction of hydrophobic lipids like triglycerides. Ethyl ether is more expensive. Petroleum ether is cheaper. With ethyl ether, since its boiling point is lower, it's more hazardous. It's prone to explosion and it's more hazardous. And then, but petroleum ether has higher boiling point, which makes it less flammable. And then ethyl ether is hygroscopic. So over time, because it absorbs moisture, it loses its efficiency. So what can we do? We can combine these two solvents together and use that combination at the ratio of 1:1 or different ratios. The first method of fat analysis or extraction, which is based on solvent, is Goldfish method. Don't ask me about the relation between this name and the method. I don't see logic, but it's called Goldfish method. So you have a plate. You add your solvents here. And then you have a glass compartment, and there is a compass. There is another part here that you can put your sample in a thimble and put that thimble in this glass, and then they get completely face each other. You turn on the hot plate, and then the solvent evaporates, goes up, and then again gets back. You don't have any soaking step in this method. So your sample is in the thimble, you put the thimble and then turn on the hot plate. So there is no time for your sample to completely get soaked with the solvent. And that might make an issue, which is channeling. That means the solvent goes to your sample, then it evaporates, condenses, get back without extracting the fat. That is one thing one issue we have with this. But this method is continuous. It's a little bit faster than other, semi-continuous like succulent method. And it's a common method. Succulent, which is a semi-continuous method. So you have your hot plate. Each section is like this. You have your heater or hot plate, and you have a boiling flask. Then you add your solvents here. There is another middle glass compartment in this part, and then you can put your sample, which must be pre-dried, your dry sample in the thimble, and then put it here. And then you see there is a siphon arm here. and there is a condenser which has an outlet and inlet for water, for cold water. So once, and then you add some solvent here and give it time, like 30 minutes, 15 minutes, 1 hour, so that your sample gets soaked with solvent. And then you turn on the heater and the solvent starts evaporating. And once the height of solvent gets here, siphon back to the boiling flask. It's a semi-continuous method. Your sample should be dry. It's an AOAC method. Both these methods are gravimetric methods. And then once the procedure is complete with Succulent, it takes between 5 to 8 hours to get complete. And once the procedure is complete, you can take the thimble out and let it dry and wait based on the difference in the weight of the thimble or your thimble, because you put your sample directly in the thimble. Based on the weight difference in thimble after drying and before in the initial step, you can determine the weight of your fat or fat content. Here is a question for you. If the fat percentage on dry basis is 15%, what would be the fat percentage on wet basis if moisture content is 20%? It's simple. It doesn't need any hints. So just determine the this 12%. Yes. So 20% moisture in wet basis. So your total solid based on wet basis is 80%. 15 times 80% is 12%. And always a hint for you to check yourself and see if your result is correct or not. Always when you are doing the math, dry basis, if you are calculating fat percentage, protein percentage, whatever, based on dry basis, it should be higher than wet basis. So now, 12% is less than 15%. 15% was based on dry basis. So your result is lower. It's correct. If it was 16%, then you should know something is wrong in your calculations. Okay. Mojonnier or model. This is another method based on solvent extraction. It's an AOAC method, and it is a discontinuous method. And it's a gravimetric method. So Goldfish, Succulent, Mojo are gravimetric. So the meaning of discontinuous. You have your Mojo flask, add your sample, just once add your solvent. Do that step again, the second solvent. It's not a continuous system that solvent gets back to your sample and then again evaporates and gets back. Just once. You do each step once and that's it. So it's a discontinuous method. And we usually use combination of ethyl ether and petroleum ether to make sure we extract all the fat and we do not do underestimation. The other thing with this method is that you can do it as on your wet sample. It doesn't need to get dry. You don't have to do it on a dry sample. So it's a plus, less work. But here is the point. If you have a complex sample which has high protein or high carbohydrate content, this method allows us to do digestion and make sure we break down the bonds between fat and protein or carbohydrate. How? If you use ammonium hydroxide, you are doing an alkaline digestion that breaks down the bonds between protein and lipid because it precipitates the protein. And then if you have a sample like a flour, which has high fiber and carbohydrates, then you can use acid digestion. Use hydrochloric acid to do acid digestion and break down the bonds between carbohydrate and fat. And also it helps to breaks the bonds between protein and fat as well. So depending on your sample, you can use acid digestion or hydrolysis or alkaline digestion or hydrolysis. With samples which have high carbohydrate contents, we go with acid hydrolysis and we use HCl. Elevated pressure and temperature. So they are like two methods. They are not an AOAC method. They are not an official method of analysis, but they are efficient. With supercritical fluid extraction method, it's efficient when you want to do fat extraction. Maybe this expensive method, maybe no one recommends you to do fat analysis just for total crude fat estimation. Use this method. But if your purpose is fat extraction and then you want to use a GC step after that to determine, I don't know, fatty acids and other lipid components, it's a good method. Here is the point. With supercritical fluid extraction, we use CO2, which is a gas, but we apply high pressure and temperature. So under that high pressure and temperature, CO2 converts to a fluid. It's not a gas anymore. And then you have a sample in the sample cell, fluid gets in, it's in contact with your sample for a while, and then after extraction is complete, it comes out and go to collection vial or cell. So in collection vial or cell, you have the fluid and the fat. Here is the point. In this cell, you have high pressure and temperature. Once the fluid gets out, there is no pressure. You remove the pressure. And so CO2 fluid converts to CO2 as a gas. So you don't have that supercritical fluid anymore. You have the gas. And then because of a little bit high temperature, CO2 evaporates, it's a gas, and then you'll have your fat so that you can weigh it, collect it, weigh it, do further analysis you want to do. So, yeah. Any questions so far? No? The other method with high pressure and temperature is accelerated solvent extraction or AS. So again, here we don't use a gas. We directly use a solvent, which is usually a non-polar solvent. The another solvent. The solvent gets to the extraction step, in which we have our sample. So again, we have high pressure. High pressure increases the boiling temperature of the solvent. So the solvent doesn't evaporate easily because of high pressure. And so extraction happens here. And then there is a valve between extraction unit and collection vial or cell or unit. Depending on this valve situation, we can do the extraction under static, dynamic, or static or dynamic condition. If the valve is closed and then we open it after a while in a specific time frame or gaps, then we are doing extraction under static condition. If it's open, then it's dynamic. And if we open it and close it at different times, then it's a combination of these two, semi-static or semi-dynamic. So in the static, we open the valve in the end of extraction, once it's done. In semi, we open it and close. If you are working under dynamic conditions, then solvent use is a lot. You are using a lot of solvent. And then once it gets here, again, because there is no pressure here, the solvent evaporates. And then you have that here. You can dry it and wait and then determine the fat content of your sample. Non-solvent extraction methods. There are two common methods, Babcock and Gerber. So this is the common method for dairy products, milk, cheese, and cream. We use this one for cheese because it's more, solid and it's hard to, use this way. We add it over here. So it's this method is a volumetric method. So you have your sample inside, 5 ml, 10 ml volumetric, and then you add sulfuric acid. Sulfuric acid, since it's acid, it digests protein, and that digestion, that breakdown in the bonds, results in higher temperature. And because of that high temperature, it helps fat get released or extract. And then you centrifuge. Once it's done, you centrifuge. And so fat has lower density compared with other food components. So fat moves to the upper here. And this part is like a gradual cylinder. So you can read volume half here and determine, okay, I have like 3 ml, 2 ml fat in my sample. And you don't need to dry your sample. So less work here. Gerber method, again, it's a common method for dairy products, especially for milk and some cheese samples. So it's similar to Babcock method, but there is a difference. In Babcock method, we don't use any alcohol. But here in Gerber, we use isomyl alcohol. And the reason we use it, okay, if you have high sugar content in your sample, like a chocolate milk, a chocolate cream, high sugar content, once you add sulfuric acid, it blackens your sample because of charring. And then it makes reading the volume really hard. So if your sample has high sugar or some sugar additives, it's good to work with Gerber method because we are using isomyl alcohol that prevents that charring and doesn't allow your vessel get black. A question for you. So these two methods, Gerber and Babcock, are volumetric method. This is important. So that helps you in your calculations. If you know density of your sample and it's fat, then you can use it to convert volume to mass. So I said the answer. You know the answer now. And now you need to do a simple math. If milk fat density is 0.9 and milk density is 1.032 gram per ml, and if the fat percentage on a volume basis is equals 3.55%, what would be the percentage of fat based on wet basis? What would be the percentage of fat based on wet basis? So you have the density of fat, you have the density of milk, you have the volume of fat in your sample, in your milk sample. Just convert it to mass based on gram, and then tell the fat percentage in your sample. And again, because it's wet basis, you work based on, whatever it is. Okay, I can give you like 1 or 2 minutes. Three point. My calculation was 3.1, but probably you are close to it. Yeah, probably you're right. Great. Any other? Okay. So let's do it together. So fat percentage volume in your sample is 3.55%. That means you have 3.55 ml fat in your sample. Then you have the density. I show density like this. You can show it with D. Density of fat in your sample is 0.9, yeah? 0.9 gram per ml. So what is density? Weight? Actually not weight, just mass of yours to the volume. and the volume of fat was 3.55 ml. So the mass of fat you have here is 3.195 grams. Again, you have density of the milk as well, which is 1.032 gram per ml. And the milk was 100 ml. So based on this fat content was for 100 ml of milk. So you have 100 ml of milk. What is the mass? It is 103.2 grams. Okay. Then percentage of fat percentage based on wet basis. You don't need to convert it to dry basis. So fat weight based on wet basis equals 3.195 here gram to 103.2 gram times 100, which is 3.1%. Is it clear? If you have any question, ask. No question? Okay. And you have the calculation here. Do you need this slide? Do you need us to wait more on this slide? Just, okay. Instrumental method. These are not official methods, but they are fast. They are really, really fast. Once you do the setup, setup is time consuming, but once you do the setup, they are really fast. So they are good for quality control purpose. They are not, you cannot use them for nutritional labeling. No. IR, NIR, and NMR, they are spectroscopy methods. So I know IR was not covered, yet, has not been covered yet, It's for the next lectures. I think so. It's after approximate analysis. So with IR, which is a spectroscopic method, you work on at a specific wavelength or wave number. So the fat absorbs light at a specific wave number or wavelength. And then whatever the fat content is higher, the absorbance is higher. So you can use IR and NIR for fat measurement to determine the fat content, but once you're doing it, you need to do an official method as well. You need to use Solvent or Mojo as an official method to provide you a calibration equation. So you prepare your samples with different fat content, one specific sample with different fat content. You measure the IR absorbance or NIR absorbance, and then you measure the fat content with Mojo or Solvent. So Mojo tells you sample A has 2% fat, sample 2 has 4% fat. And then you do the same fat analysis with IR on the same samples. Okay, with Mojo and or Solvent, you know that sample A had 2% fat. That 2% fat resulted on certain amount of absorbance in IR. 4% fat resulted in another absorbance. And then you can have a calibration equation based on that. And once you have the calibration, you can use IR for fat measurement in your sample. So for each specific sample, you need to have a calibration equation using an AOAC method, like Mojo or SAX. NMR is a complex method, but once you have it set up, it's really, really robust method. Phosphate method is not a common method, but and it's based on a specific gravity of your sample, which is extracted by a solvent. So there are different charts that convert specific, based on different oils and fats, they convert specific gravity to fat content. So if you're using phosphate method, you need to have those charts. So they convert specific gravity of your fat, which is extracted by a solvent, to fat content. It's not a common method and it's not an official method of analysis. I think that's it. And yeah, thank you. If you have any question, ask. You have time. No question? Good. Try to stop sharing. Send before.
And then stop.